Today, I will explain in more detail how we sample population parameters from the uncertainty distribution in Simulx. In the feature of the week 124, I have explained you how to use the elements MLXPOP uncertain lin and MLXPOP uncertain SA to take into account the uncertainty of the population parameters. In this video, I will explain to you how the sampling is done exactly. This is a more technical video for our users who want to know how it works behind the scene. Let's first check the information contained in this element. If I click on View, I see first for each population parameter the value estimated by Monolithics and the relative standard error RSE. They are the same as displayed in the Monolithics graphical user interface here and here. The RSE represents the uncertainty of the corresponding population parameter, but it is not sufficient to sample sets of population parameters because it does not contain information about the correlation between the estimated values. This correlation is indicated in Monolithics in this matrix here. In this example, for instance, I see that the error model parameters A and B have a strong negative correlation, meaning that I can have a large A and a small b, or the opposite, but not both A and B large. The correlation matrix is a good way to visualize the strength of the correlations because all values are between -1 and 1. But if I want to sample from the uncertainty distribution, it is easier to work with the variance-covariance matrix. The correlation matrix is related to the variance-covariance matrix by the following formula. You see that with the standard errors and the variance-covariance matrix, I can calculate the correlation matrix, and in the other way too. So in Monolithics, we display the estimated value, the standard error, and the correlation matrix. And in Simulx, we have the estimated values and the variance-covariance matrix, which gives the same information. Note that the RSE values in Simulx are just shown for your information, but they are not used directly. In Simulx, these values are saved to the .mlx file, as you can see here, and these values cannot be edited. If I close the object, you see that I have no edit nor duplicate button. The variance-covariance matrix defines a multivariate normal distribution from which it is easy to sample from. Let's focus on the two first parameters, for instance. The multivariate normal distribution could look like this. However, if I sample a K-pop value from a normal distribution and the uncertainty is large, I may end up with a negative Ka-pop value. So to avoid this, we transform all population parameters so that the transform parameter can take any value from -infinity to +infinity. So for Ka-pop and V-pop, this would be log Ka-pop and log V-pop. And we do the sampling in this Gaussian space. Actually, the matrix that is displayed in Simulx is directly in the Gaussian space. So the procedure is to first sample the transform parameters in the Gaussian space from the multivariate normal distribution, and then to back transform the sampled values to the usual space. The underscore pop parameters are transformed according to the individual parameter distribution. So log Ka-pop if Ka has a log normal distribution, for instance. The beta parameter for the covariates can be positive or negative, so they are not transformed. The omega parameters should stay positive, so they also have a log transform. The correlation parameter should stay between -1 and 1, so we apply a logit transformation to them. And finally, the error model parameters also have a log transform. So once we have sampled in the Gaussian space and transformed the values back to the usual space, I have a collection of population parameter values sets that represent the uncertainty and that I can use for the simulation. There is one difference between Monolithics and Simulx that I would like to address. In Monolithics, internally we always work in the Gaussian space. So we calculate the variance-covariance matrix in the Gaussian space. To calculate the variance-covariance matrix in the usual space, we multiply the matrix on both sides by the Jacobian. The Jacobian contains the derivatives of the transform parameters with respect to the usual parameters. So for log transform, it would be the derivative of the log, so 1 over Ka-pop, for instance. And then the standard errors that you see in the Monolithics graphical user interface are the diagonal elements of this matrix. On the other hand, when you export the Monolithics project to Simulx, we export the matrix in the Gaussian space, sample from it, and then back transform. The standard deviation of all these samples represents the uncertainty of the population parameter values. And the standard error in Monolithics also represents this uncertainty, but it is not calculated in the same way. When the relative standard errors are pretty large, the standard deviation of the values sampled by Simulx is often larger than the standard error shown in Monolithics. This is normal, and it is because the Jacobian is just a first-order approximation. The last point I would like to mention is about correlation parameters. Let's assume that I have three correlation parameters between Ka and V, Ka and Cl, and V and Cl. These three correlation parameters form a matrix that needs to be definite positive. If we sample values for these three parameters from the variance-covariance matrix of the estimates, we have no guarantee that the matrix that will form will be definite positive. So this is something that we check after the sampling, and if the matrix is not definite positive, we sample again. Now you know everything about the sampling from the uncertainty distribution. Have a nice week.